We have seen a few examples of situations involving objects and their relationships by drawing a diagram of points with segments joining those points that are related. Now let's define the mathematical object that we use to describe those situations. Here's the definition of graph. A non-empty finite set V along with a set E which contains two element subsets of V. You can think of a graph as a mathematical object made of two parts. The first part is a set of vertices, then the second part is a set of edges. Each edge is a subset of the set of vertices containing two distinct vertices. Now we have some remarks about the definition of a graph. In a graph, we don't allow loops. A loop is a connection from a vertex to itself. Later, a loop will be considered an edge, but in a different context. We also don't allow parallel connections between two vertices. So here is an example. The graph G here is made of two parts. A set of vertices A, B, C, and D, and a set of edges A, B, B, C, and C, D. Notice that each edge is a subset of the set of vertices. So in fact, each edge, for example, edge AB, is actually a subset. It's a two-element subset of the set V. Since it's a set, then it doesn't matter if you represent it by AB or BA. The order in a set doesn't change the set. So in reality, the set E is made of two-element subsets, AB, BC, and CD. But to simplify the notation, we'll simply get rid of the braces and represent the edges by AB, BC, and CD. Another remark about the set of edges is that each edge is a subset with two distinct elements of V. This way, we will not have loops in a graph. Again, loops are connections from a vertex to itself. So if we try to create a subset with two elements A, it will be a subset with just one element, since repeating elements in a set is not allowed. So this is not possible. This is not an edge in the set E, which means no loops here. Graphically, this is represented by points on the plane, and the edges are simply segments. Here's the edge AB, or BA, since it's a subset. It's a two-element subset of V. It doesn't matter if we refer it to as AB or BA. It's the same edge. Here's BC, edge CD or DC. And this is a graphical representation of a graph. We can represent the same graph this way and in many other ways. Here are more definitions. Here's the edge AB again. Now, E, lowercase e here, represents edge AB. If E joins the vertices A and B, we say that A and B are adjacent. We also say that edge E is incident with A, and edge E is also incident with B. Here's the definition of degree of a vertex. The degree of a vertex V is the number of edges that are incident with the vertex V. In this illustration, we can see that the degree of A is 1, since there is only one edge incident with the vertex A. The degree of C is 2. There are two edges that are incident with C. Finally, we have a theorem, Theorem 4.1 in the textbook. It says that in any graph, the sum of the degrees of the vertices is twice the number of edges. If we go back to this example here, let's add all the degrees. Degree of A is 1, degree of B is 2, degree of C is 2. Degree of D is 1, so 1 plus 2 plus 2 plus 1 gives us 6. Now, if we count the number of edges, 1, 2, 3, and multiply by 2, that gives us also 6. The theorem is saying that the sum of the degrees is simply the number of edges times 2. Now, why is that true? It's very easy to prove this theorem. If we add all the degrees, we're counting the same edge twice. For example, when we add the degree of A and the degree of B, we're counting this edge twice because the degree of A counts this as one edge that is incident with A, and the degree of B counts this edge again because that edge is incident with B. Here's another example of a graph. Described by Kn, this is a very important graph. It will be used several times throughout this semester. The complete graph is a graph where every vertex is joined to every other vertex in the graph. Here is a complete graph with 3 vertices, K3. Notice that this vertex is connected or is joined to every other one, which are B and C. Same with B, B is joined with A and C is joined with B and A. Here is K4. A is joined to every other vertex, B is joined to every other one, and so forth. K4 here is represented in a different way graphically, but it's the same graph. Other representations of graph include adjacency matrix. An adjacency matrix is made of entries of zeros and ones. Now here is an example of a graph. And here's the adjacency matrix. Each row represents a vertex. Each column also represents a vertex. First column here, for example, represents the vertex A. First row represents the vertex A as well. Now, at each entry of the matrix, we have either 0 or 1. 0 means that there is no edge connecting vertex A to vertex A. In fact, since we don't allow loops in graphs, there is no edge from A to A. Now, there is an edge from A to B, so at row A, column B, we put 1. That's because there's an edge there. And you can also read column and row. Edge BA is the same as edge AB. This means that this matrix is symmetric, meaning that everything above the diagonal of the matrix, so here is the diagonal, everything above the diagonal is reflected below the diagonal. Here is 1, then we have 1 there. Here is 0, then we're going to have 0 there. Here is 1, then we're going to have 1 there. Here's the adjacency matrix. Now, theorem 4.2 says that the sum of the entries in the row is the degree of the vertex corresponding to that row. Let's go back here. If we add all the entries of this row here, row B, 1 plus 2, 1, 2, that's the degree of B. Well, that's because each number, 1 in the matrix, represents an edge. If we're adding all the 1s in this row, we are adding all the edges that are incident with B. And that's the definition of a degree of a vertex. In this case, the degree of B. Another way to represent a graph is through adjacency lists. Now, adjacency lists simply lists each of the vertices followed by the vertices that are adjacent to it. So here is the adjacency list of this graph. First, we list the vertex A and all the vertices that are adjacent to A. And that's only B. Here now we list vertex B, followed by all the vertices that are adjacent to B, which are A and C. And we keep doing that for all the other vertices.